if f of t equals x of ti plus y of tj plus z of tk, which is of course the general form of a vector function of three variables in three-dimensional space, then let's ask ourselves, what is the meaning of f prime of t? Or how do we calculate f prime of t? Now we pretty much already know because we've already done that, but let's show that we've been justified in what we've been doing. So f prime of t is the limiting value of delta f over delta t. So let's start by writing what we would mean by delta f over delta t for this function. Well, delta f over delta t, of course, is f of t plus delta t minus f of t divided by delta t, and that's going to be equal to what? Well, f of t plus delta t is x of t plus delta t I plus y of t plus delta t j plus z of t plus delta t k. This, I don't have room to string it all out, so I'm going to kind of group my numerator. I'll start a bracket here so we know when the bracket ends, the numerator ends, but that will be minus the quantity x of t I plus y of t j plus z of t k quantity, and we'll put that in brackets, and then we'll indicate that all that is divided by delta t. So we've just written literally out what f of t plus delta t is, what f of t is, and written them in the appropriate places within this expression. Now, we can combine our I components, and very clearly, if we add the I component here to the I component that we get here, I am skipping a step. I haven't distributed the negative through there, but I think we understand that that's going to happen. We're going to get x of t plus delta t minus x of t multiplied by I. And I'm also going to distribute my division by delta t. So I'm going to have this over delta t. And then on the j component, we're going to have y of t plus delta t minus y of t divided by delta t, and that is times our j vector. And then we're going to have a very similar term for the z. We could write this, if we wished, as delta x over delta t times I plus delta y over delta t times j plus delta z over delta t times k. So that when we take the limit as t approaches 0 of delta f over delta t, crowding ourselves a little bit here, we get, now I'm going to put a few dots in here to indicate that there's something that I'm leaving out that needs to be justified that we haven't talked about but that your text does talk about. If you're familiar with the property of limits, and this is delta t goes to 0, not t goes to 0. Okay, the limit is delta t goes to 0 of delta x over delta t multiplied by I plus the limit as delta t approaches 0 of delta y over delta t times j plus the limit as delta t goes to 0 of delta z over delta t multiplied by k. Now the dots in here, I'm distributing the limiting process through a sum, and then I'm also factoring a constant vector I out of the limit of what we get from this term. Technicality, but it's important in many cases to worry about the technicalities and to develop the ability to consider those technicalities. Now, a little more hand waving here, but the limit as delta t goes to 0 of delta x over delta t is what? That's just x prime of t. So we have x prime of t I plus y prime of t j plus z prime of t k. This is an outline of the proof, and what this proves is that for any function of this form, a function times I plus a function times j plus a function times k, giving us our overall vector function, that if we want to take the derivative of this function, all we have to do is treat the I, j, and k as components and take the derivative of each term. And that's, of course, what we've been doing all along. But again, it's important to have the theoretical justification and to know that these operations that we're doing make sense.